Everyone, this video is going to go through question number 4 from the 2018 AP exam. And so what we have here is a table of values. The function we have is the height of a tree at time t given by a twice differentiable function h, and select values of h are given in the table. So the first part, A, is asking us to use the data in the table to estimate h prime of 6. So we're estimating the derivative, and so to estimate the derivative, we're going to use the average rate of change, or just the regular old slope. So we're going to pick the closest interval around 6 to do that. So in this case, h prime of 6 is going to be about h of 7 minus h of 5 over 7 minus 5. So we get 11 minus 6 over 2, or 5 halves. And our units here are going to be meters per year. So now it says to interpret the meaning of h prime of 6 in the context of the problem. So h prime of 6, the derivative, right, we know is the instantaneous rate of change. So in this case, it represents the rate that the height of the tree is changing at the given time t equals 6. So h prime of 6 represents the rate at which the height of the tree is changing. We're going to give units for that. So measured in meters per year. And then we have to give the time. At time t equals 6 years. Okay, so for scoring on this exam, they gave 1 point for the estimate and then 1 point for a correct interpretation. All right, part B, it says explain why there must be at least one time t on the interval between 2 and 10 such that h prime of t is equal to 2. Now, as soon as you see them asking you to guarantee that a function takes on a specific derivative, that should make you think about the MVT, the mean value theorem. And so remember, for the mean value theorem, we have 2 conditions that we have to check. We need to check if our function is differentiable and continuous. And then we have to check if at some point, if the average, over some interval, is the average rate of change equal to 2. Because if there is an interval where the average rate of change is equal to 2, and we have a continuous and differentiable function, then we can guarantee that the instantaneous rate of change is 2 at some point in that same interval. So let's go ahead and see what we've got here. So the first thing I need to check is what do we know about this function h? Well, if we go back here, it says my function h is twice differentiable. Well, then what we know is if our function is differentiable, it has to be continuous. So I'm going to say since h is differentiable, it is also continuous. We know that in order to be differentiable, you have to be continuous. So we've met our first criteria. Now I want to check on the average rate of change. And so normally we'll just start with the interval that's given here. So I'm going to check this average rate of change, h of 10 minus h of 2 over 10 minus 2. And we'll use our table here. So h of 10 is 15, h of 2 is 1.5, and then this is over 8. So it looks like I get 13.5 over 8, which actually is not great. I was hoping it was going to be equal to 2. So let's see what's happening here. That doesn't mean that I failed on the MVT. That just means I might have to look over a different interval. So I'm going to kind of cross this out here because that didn't get us where we want to be. So let's see. I'm looking for an average rate of change of 2. And here's what I notice. If I look over the interval from 3 to 5, so I'm going to do h of 5 minus h of 3 over 5 minus 3. So h of 5 is 6, h of 3 is 2 over 2 equals 4 over 2, which is equal to 2. Now I've got an average rate of change that's equal to 2. And since the interval from 3 to 5 is within the interval from 2 to 10, we're still okay here. So since we've got a function h that's continuous, we've got this interval here where the average rate of change is equal to 2, we can say, therefore, by the mean value theorem, there exists a time t. Now, we used this interval from 3 to 5, which is okay because, again, that interval still lies within 2 to 10. So there's a time t in the interval from 3 to 5 such that h prime of t equals 2. So this one was a little bit unique in that we had to actually find an interval that would serve our purpose of giving us an average rate of change equal to that instantaneous rate of change. So for scoring here, they gave 1 point for identifying the average rate of change over that interval, and then 1 point for your conclusion, which cites the mean value theorem. All right, the last part to this, there was another part, but we cut it out because it went along with Unit 8. So the last part for us says the height of the tree in meters can also be modeled by this function g with this equation, where x is the diameter of the base of the tree in meters. So I'm going to make a note here just to keep track of my variables. X is the diameter of the base. And what else do we know? G is the height of the tree. All right, when the tree is 50 meters tall, the diameter of the base of the tree is increasing at a rate of 0.03 meters per year. So I want to make a note here. This 50 meters tall has to do with G. This rate here, 0.03 meters per year. I know I'm marking this up a little bit. It says the diameter of the base of the tree is increasing at a rate. So that's going to be our dx dt because it goes along with the diameter of the base. According to this model, so what is the rate of change of the height of the tree with respect to time at the time when the tree is 50 meters tall? Again, when I see this here, the rate of change of the height of the tree with respect to time. As soon as I see that, I should be thinking about a related rates problem. So the rate of change of the height of the tree with respect to time. Well, the function I have for the height of the tree is this g of x. And I know that's 100x over 1 plus x. So I want to change over to blue here. So now I need to differentiate with respect to time. So here I'm going to get dg dt. Now here I have to be careful because I need to use quotient rule when I'm finding the derivative. So I'm going to make a note that this is going to be quotient rule. And I also have to remember my implicit. I'm differentiating with respect to t. So let's do this. So quotient rule says low, so 1 plus x, d high, well my derivatives is 100, and then I need a dx dt, minus high, 100x, d low. The derivative of that is just 1, but then I need a dx dt all over low squared. All right, so let's see what quantities we need here. We've got x, I've got dx dt, and a dg dt. Now we want the rate of change of the height of the tree with respect to time. That tells me dg dt is our unknown. We identified our dx dt. That was our 0.03. And now the question is, what is x? So let's see. X was the diameter of the base of the tree. I don't know that. All right now I know is I do know that g of x, my g at this point is 50. So I'm going to use this equation here, and I'm going to use it to solve. So when g is 50, we're going to use that to solve for what x is at that point in time. So 50 equals 100x over 1 plus x. So to solve, I'm going to multiply by 1 plus x on both sides, which is going to give me 50 plus 50x equals 100x. If I subtract 50x, I get 50 equals 50x, and so x is equal to 1. So now I have what I need to be able to go back and solve. So I've got dg dt, that's my unknown, equals 1 plus 1 times our 0.03 minus 100 times 1 times 0.03 all over 1 plus 1 quantity squared. So now I've got, oops, I missed something here. It should have been 1 plus 1 times 100 times 0.03. Okay, so now I've got 200 times 0.03 minus 100 times 0.03 all over 2 squared, which is going to be 4. So if I simplify this, that's going to give me just 3/4. And then my units here would be meters. Let's see, what was it? Meters. And then the time was measured per year would be our final answer. So scoring for this particular year, they gave 2 points here for dg dt, and then 1 point here for the final answer. All right, so hopefully that helped address any questions that you have, but obviously if there's anything you're still wondering about, please feel free to reach out to your teacher. Thank you.